Okay, thanks to everybody for joining the class. Today we'll discuss the properties of Fourier transforms and application of Fourier transforms, especially in heat equation, wave equation. Uh, so the application of Fourier transforms is the main issues of this class. The properties of Fourier transforms, first one is linear property, and then change of scale property and shifting property, then these three properties is the main properties of Fourier transforms. First of all, linear property. If the first Fourier f1 as means the Fourier transform of the uh, first Fourier transform, and this is the second Fourier transform. Fourier transform of this first function, and this is the second function respectively. Then the combinedly, if we take the Fourier transform of a f1x plus b f2x, a and b are the constant, then if we can prove a f1s equal a multiply first Fourier transform of the first function plus b into Fourier transform of the second function. This is the actually linear property where a and b are the constants. Now we'll prove we know Fourier transform equals to 1 by square root over 2s pi minus infinity to plus infinity e to the power is x first function f1x dx. Actually, this is the from the definition of Fourier series, complex form of Fourier transform. And the second Fourier transform of second function f2x equals to f2s equals to 1 by root over 2s pi minus infinity to plus infinity e to the power isx f2x dx. Now just putting the values here, just changing the functional values. uh, Fourier transform of f1x and plus b into f2x equals to 1 by root over twice 5. Just changing the variable one, just changing the functional values f1x plus bf2x. Now just multiplying this e to the power isx on both one and taking this integration to every functions, then we get two terms of integration parts. Therefore this equals to f1s plus bf2. Very easy for you, just putting the values of functional values, we get the proof. Now changing scale of property, change of scale property. If fs is the complex Fourier transform of f of x, then f of a into x, that means functional value will be x. This is the f of x equals to 1 by a Fourier transform of s by a. This is the Fourier transform of s by a. This is the change of scale. Actually this a can change to 1 by a, inverse inverse constant, and the parameter changing s to s by a. This is why it is called change of scale property. Now we know that Fourier transform of parameter s equals to 1 by root over twice pi minus infinity to plus infinity e to the power isx f of x dx. Now if we take the Fourier transform of this function f of x equals to 1 by root over twice pi, just changing this x to x only, and this is the complex form. Now put ax equals to t, then dx equal to will be dt by a. Therefore just substituting this to this integration, 1 by root over twice pi minus infinity to plus infinity e to the power is, this x equals to what will be t by a, x equals to t by a, just changing. Now the function will be f of t dt by a. This is why 1 by a, 1 by root over twice pi minus infinity plus infinity e to the power I s by a into t. That means this is the main variable s by a parameter, the parameter shifting parameter. This is, then this whole integration indicates the Fourier transform of s by a. Just inside the bracket, inside the first bracket, this is the Fourier transform of this one. This is why 1 by a f of s by a. This is the proof of change of scale property. Now shifting property, Very interesting property. If f of Fourier transform of the complex Fourier transform is this, then f of Fourier transform of f of x minus a, that will be e to the power isa f Fourier transform of f of x. Now from the definition of Fourier transform of f of x will be f of s equals to minus infinity to plus infinity e to the power isx f of x dx. Now just changing the function s parameter, changing this parameter f of x minus a, we get like this function f of x minus a only. Now if we put x minus a equals to t, then dx equal to dt. Just substituting these values inside the integration minus infinity to plus infinity e to the power is, just x equals to what will be t plus a. From this substitute values is t plus a, then f of t dt. Now e to the power isa, separating exponential function from this total power, e to the power isa divided by root over twice pi minus infinity to plus infinity e to the power ist is the t is the main variable here. This is why it will be the Fourier transform of f of s. This is why it is called shifting property. Understand everybody? Mm, Now this is the main important theorem of this Fourier transform. Convolution. What is convolution? The convolution of two function f of x and z of x. There are two given function, is defined as the product of these two function, and it is represented by an integral function minus infinity to plus infinity f of u z of x minus u. That means x is substituted by u parameter, and x in function, in z function, this x is substitute to x minus u, and this is the integration with respect to u. U is the another parameter. This is called convolution of these two function. Actually this is the representation of two product of a function in a infinite integral form. This is also Fourier transform, convolution theorem on Fourier transform. Now actually convolution theorem can be applied into Fourier transform like this theorem. The Fourier transform of the convolution of these two is the product of their Fourier transform. Just if we take the product of the function, then we will get another product of their Fourier transform. This will be equal. We have to now prove this result. Now we know that this is the from definition of convolution. Convolution from f of x into z of x equals to 1 by root over twice pi minus infinity to plus infinity f of u z of x minus u. Remember it, not u minus x. This is the du, and this integration with respect to u. That means u is the independent variable here, and u is the independent variable. Remember it. So this left in equation number 1. Now taking Fourier transform on both sides of this one, we get Fourier transform of this product function. That means convolution form f of x into z of x equals to Fourier transform of this will be, right, minus infinity to plus infinity f of u z of u x minus u du. Just Fourier transform of this equals to 1 by root over twice pi minus infinity to plus infinity. This comes from Fourier transform integral. This integration for Fourier transform. Then third bracket will be, this is the Fourier transform of what? This is look like f of x. This is why 1 by root over twice pi minus infinity to plus infinity f of u z of x minus u du. Then this is the exponential form of Fourier transform e to the power x. This whole f of x, remember it. This whole look like f of x. This is why e to the power isx dx. Now this integration with respect to x is the independent variable for here. Now within bracket u is the independent variable. Remember it. Just this whole termed as f of x. Remember it. In the second bracket, inside the bracket, whole term in look like seems to be f of x. Now 1 divided by root over twice pi minus infinity to plus infinity f of u du. Just separating f of u du here, 1 by root over twice pi minus infinity to plus infinity, and z function and exponential form e to the power isx dx, second bracket. Now 1 by root over twice pi minus infinity to plus infinity f of du dot this whole can be written as f of z of x minus u by shifting property. This is the whole Fourier transform of what? Fourier transform of z of x minus u from definition of Fourier transform. This second bracket can be written as Fourier transform of z of x minus u. Remember it. Fourier transform of this function. Now 1 by root over twice pi minus infinity to plus infinity f of u du. Now this Fourier transform can be written as e to the power I u as zs by shifting property. We have already proved this property where shifting property, just shifting property, this one shifting property. That means f of Fourier transform of f of x minus a equals to e to the power I as a f of s. Remember it. This is the shifting property, just exponential form. This function, uh, this integration transform to e to the power I as a Fourier transform of f of x. This is why it is called shifting property. Now we have used here shifting property, like 1 by root over twice pi minus infinity to plus infinity f of u du e to the power I u s zs. Zs is used for shifting property, e to the power I u s and zs f of s you cannot use because f of f capital F used in left hand side before. This is why we used here only zs to represent Fourier transform. This is also Fourier transform of f of x. Now this equals to z as the dot, that means product of this one, 1 by root over twice pi minus infinity to plus infinity f of u du, then exponential form. But this whole variable with respect to u, and this is whole also can be represented as Fourier transform of f of s. That means zs is the product of f of s. F of s is the product with zfs. These two Fourier transform. This is the Fourier transform of first function. This is the second function. By inversion, we can take inverse Fourier transform equals to this one f of dot z, just f dot z, f dot z. This will be the inverse one. F comes here, taking inverse on both sides. Then f inverse of this will be f dot z, and f inverse of f of s dot f inverse. They're just taking product one, product function. This is the proof of convolution theorem of Fourier transform. Now, Parseval's identity for Fourier transform. We have already finished in our previous lecture Parseval's identity for Fourier series, but now Parseval's identity for Fourier transform. Just a little bit difference here. Now, what's the statement is for this Parseval's identity? If the Fourier transform of f of x and z of x be this and this, that means capital Fs will be the Fourier transform of f of x, and capital Z of s will be the Fourier transform of z of x, small zx, respectively. Then the first one, minus infinity to plus infinity, the integration minus infinity to plus infinity f of x, the g of s ds equals to minus infinity plus infinity f of x z bar x dx. Actually, this is the complex conjugate, complex conjugate of the Fourier transform of zs, and this is the complex conjugate of the function z of x. Now, where z bar is the complex conjugate of this, and z bar small z bar x will be the complex conjugate of small zx. Now, in secondly, minus infinity to plus infinity f of s, Fourier transform of f x whole square ds equals to minus infinity to plus infinity f of x modulus whole square dx. This will be the identical, and this also identical. That means one is first property is for complex conjugate form, and second was is Parseval identity. This is the actually Parseval identity, and this is identical, absolute value. But there is no absolute value. There is just Fourier transform of f of x whole square, this one, and this will be the equal of f of x modulus whole square. Now proof for one, integration minus infinity to plus infinity. This one just taking this one right hand side, minus infinity to plus infinity, f of x. Now complex conjugate what will be 1 by root over twice by minus infinity to plus infinity z bar x. That means complex conjugate of Fourier transform f of x e to the power isx dx. This comes from where? Fourier definition of Fourier transform. Now since z bar x, then complex conjugate of zx equals to 1 by root over twice by minus infinity plus infinity z capital Z bar x isx dx. This is also from complex conjugate form of Fourier transform. Minus infinity to plus infinity f of x z bar x equals to 1 by root over twice by minus infinity to plus infinity integration g bar s ds. This just separating the functional values. Since this equals to f of s, then we can write this equals to minus infinity plus infinity z bar s f of s ds. This is left for equation number 1. Putting z x equals to f of x in equation 1, then we get the second one property. This is the proved second one. Just f of x and f of x bar. What will be? From the definition of complex conjugate, complex number, we can write z into z bar equals to z modulus of z whole square. Can you write? Suppose this is z complex number and this is the z bar conjugate complex number. Z into z bar, what will be? Z absolute value whole square. That means complex number whole square you can write. So in functional values also it can be written as f of x, and conjugate of x will be f of x whole square, absolute value. This will be okay. Parseval's identity for cosine transform, just we have to use only c for to indicate cosine transform, and this is for sine transform. Just same similar notation, but f only single f will indicate Fourier transform of whole function, but if we take fc, then this is the cosine transform, and if we use s, it indicate only sine transform. So now we can solve some example with the using the property of Parseval's identity. Now example 1, first example, using Parseval's identity, show that this integration 0 to infinity x square dx divided by x square plus 1 whole square equals to pi divided by 4. That means we have to use Parseval's identity to solve this integration. Now let us consider first function f of x will be x divided by x square plus 1, and so that Fourier transform of sine Fourier f of s Fourier f of s, this is the sine transform of Fourier transform equals to pi by 2 e to the power minus s. So by Parseval's identity for sine transform, Parseval's identity, if we use just Parseval's identity, then we get from Parseval's identity 2 divided by pi 0 to infinity, 0 to infinity. If we take 0 to infinity range, then we have must be written 2 divided by pi. Then f of s, sine transform of Fourier transform whole square. This is the from the properties of Parseval's identity. This equals to 0 to infinity. This f of s equals this equals to f of x whole square. Using the Parseval's identity, this one, just using this one. Second part. Now 0 to infinity f of x modulus whole square dx. Now 0 to infinity x divided by just f of x equals to what will be x divided by x square plus 1. X divided by x square plus 1 whole square equals to 2 divided by pi 0 to infinity. This equals to what? Pi by 2 e to the power minus s whole square. Whole square means what? Absolute value whole square. Now 2 divided by pi, this means what? Pi divided by 2 whole square. That means pi square by 4. Now this integration, we have to use the absolute value inside the function e to the power minus twice s, because square power will be multiplied, both are power will be multiplied each other. E to the power minus twice s ds equals to pi by 2. Now taking integration of this e to the power x formula, e to the power x, dividing with the coefficient of x, right, with respect to s. This is why coefficient what, as coefficient -2 only. This is dividing with this. In integration, we have to divide with the coefficient of an independent variable. Now, left taking limit 0 to infinity, just we get this result. E to the power infinity means what? E to the power infinity means e to the power minus infinity equal to 1 by infinity. 1 by infinity means 1 by 1 by infinity means what? 0. This is why this one 0, and after putting 0, we'll get e to the power 0 means what? 1. This is why minus half. This is why only plus half. Now this is the result 5 by 4. Just using Parseval's identity, we proved left hand side equals to right hand side. Just x divided by x square plus 1. How many x square plus 1 here? 2 times. How many x here? 2 times. This is why we have taken f of x equals to x divided by x square plus 1. Remember it. Similarly, another example you can prove using Parseval's identity. Prove that 0 to infinity dt divided by a square plus t square bracket b square plus t square equals to pi divided by twice ab bracket a plus b. We have to prove this one. Now there are this is the multiplication of two function. How? F of x equals to e to the power at and z of x equals to what will be e to the power minus bx. This is the function we have considered. One is independent variable x, another is independent variable also x, but constant different, because there is also two constant, two different constant. One is constant a, another is constant b. This is why f of x equals to e to the power minus x, another is f of x equals to e to the power minus bx. Now Fourier cosine transform will be a divided by f s, a divided by s square plus s square. Now the cosine transform of second one will be b divided by b square plus s square. We have already in first lecture, from the first part of this lecture, Fourier transform, we have proved that the cosine transform of this one is this, and cosine transform of this one is this. This can be used as a formula also. Now by Parseval's identity, for Fourier cosine transform, 2 divided by pi 0 to infinity cosine transform of first function and cosine transform of second function will be 0 to infinity f of x into gx dx, because capital F is the Fourier transform of f of x and capital Z is the Fourier transform of what? A small gx. Remember it. Now substituting the values of fcx, cosine transform of f of x, cosine transform of z of x, and these four values in one, just substituting 2 divided by 0 to infinity, just fcs values, and zcs values also this one, ds this 0 to infinity, just putting these two function e to the power x and e to the power minus bx in replace of f of x and z of x. Right, now 2 divided by pi 0 to infinity, this whole ab and this one, product of these two equals to 0 to infinity. You can take altogether exponential form like this, e to the power minus a plus b into x dx. Now taking integration, e to the power x formula, e to the power x, just coefficient dividing with the coefficient of x. Coefficient of x what? Minus a plus b. Coefficient of x minus a plus b. This is why dividing with the minus a plus b. We get, just putting upper limit look like before, and minus lower limit, we get 0 plus 1 by a plus b. Now this integration equals to, can be written as pi divided by twice ab a plus b. Just transferring this constant to right hand side. Ab dividing by ab on both sides and dividing by 2 also on both sides, multiplying pi on both sides. This is why you get pi in right hand side. So this is the result which is desired. Now the similar example, using Parseval's identity, prove that 0 to infinity sine t by t whole square dt equals to pi by 2. This is the integration. By example, previous example, we knew that f of x equals to 1 if absolute value x is less than a, and f of x equal to 0 for absolute value f x greater than a. That means there are two x values. One is 0 to infinity, another is minus infinity to 0. Now then f of s equals to square root over 2 divided by pi sin as by ds. In example 24, we have proved this Fourier transform of this function equals to square root over twice pi sin as ds. That means there is a combination between example 24 and 33. So from this sheet, we have to solve first of all example 24, then you can prove example 33. Now using the Parseval's identity, minus infinity to plus infinity, f of t absolute value of f of t whole square dt equals to minus infinity to plus infinity, just taking Fourier transform of this one f of t absolute value whole square ds, t transform to s when we take the Fourier transform. Now minus a to a, in this range minus a to a, integration between a and minus a, what will be the value, functional value 1, dt equals to minus infinity to plus infinity. This Fourier transform, what f of s equals to what we have proved in example 24, Fourier transform of this function will be this is why we have put here in the place of Fourier transform f of s, 2 by pi for whole square, square root cancel, for a square 2 divided by pi sin as divided by as whole square ds. Now this integration what will be, only one integration, what t after putting upper limit lower limit, then we get only twice a, right? This simple integration, one integration of one will be t, then we can take t between the bracket, third bracket, putting upper limit and lower limit, then after putting upper limit a and minus a, then that's will give the result twice a, remember it. Just taking this integration, we get twice a. This equals to twice by pi. This is the constant term. This is why before integration, minus infinity to plus infinity, and sin as divided by s. Now substituting this as equals to t, as equals to t, then as equals to t, then taking differentiation, ds equals to what will be, dt. Ds equals to dt. That means ds equals to dt by a. So twice a equals to 2 divided by pi minus infinity to plus infinity sin t divided by t divided by dt by a. Now this a will be, can be written as t by a. This s equals to t by a. S equals to what, t by a, t by a here in denominator. Uh, in replace of s we have put t by a. Now this all after this a and this a will be give and 2 divided by pi will be 2 cancel, and this a only single a, and multiplying by pi on both sides we get a pi. This equals to a into minus infinity to plus infinity sin t by t. This a comes from, there are two a, this is why only single a here. Now minus infinity to plus infinity sin t by ta dt, and this a also cancel. Now pi equals to this one. This integration can be written as this pi by 2, just dividing by 2 on both sides, 0 to infinity, because minus infinity to plus infinity can be written as 0 to infinity 2 into 0 to infinity. This is why 2 present here. Understand everybody? Minus infinity to plus infinity can be written as 2 into 0 to infinity, 2 into 0 to infinity, and these 2 dividing by on both sides pi by 2. This is the result. Similar process you have to prove example 34, like the example 33. Similar concept used here. I am not discussing this. This is left for you. You can try it at home. And also by using Parseval's identity, example 35. This is left for also for you. Next, Fourier transform of derivatives. Actually, inside the Fourier transform there are integration, but it has also derivative property. We have already seen that Fourier transform of f of nth derivative of f(x) equals to minus is whole to the power n Fourier transform of f of x. This property we have already seen and proved also. See the previous lecture. Therefore, Fourier transform of second partial derivatives of u will be what? Is whole square. Just in replace of n, we have put here only what? 2. Second derivative, this is y, and f of ux. Just s replaced u, and this is with respect to u. This equal to minus s square u. U is the Fourier transform of u bar is the Fourier transform of u with respect to s. Now cosine transform of first derivative, cosine transform of cosine Fourier transform of first derivative f of x will be minus root over 2 divided by pi f of 0 plus s into a sine transform of f of s. Actually, just we remember these derivatives. Now there is a relationship between Fourier transform and Laplace transform. This is very important for you. Relation between Fourier transform and Laplace transform. Now consider f of t equals to e to the power minus st zt for t is greater than 0. If t less than 0, then 0. Considering this function, the Fourier transform of f of t can be written as Fourier transform of f of t equals to 1 by root over twice pi minus infinity plus infinity e to the power ist f of t dt equal to 1 by root over twice pi 0 to infinity e to the power ist f of t dt. This is the from the definition of Fourier transform. Now minus infinity to plus infinity, just taking 0 to infinity, giving single 2. This will be root over, there is a wrong printing mistake, maybe 2 by pi root over, this will be 2 by pi root over, remember it, because 0 to infinity, and this given function 0 to infinity, this is the main function e to the power minus ist zt, e to the power minus ist zt, putting p equals to x minus is and 1 by root over twice by Laplace transform of zt, function zt, Laplace transform. Now this can be written as this one, which gives the Laplace transform of zt. Fourier transform f of t equals to 1 by root over twice pi. This is the Laplace transform. I is absent here. I is absent. This is why this is called Laplace transform of zt. Remember this relationship. Now we will discuss the solution of boundary value problem by using integral transform. That means by using Laplace transform, Fourier transform. By using Fourier transform, we can solve heat equation, heat conduction problem, wave equation problem. Now we see the application of Fourier transform. Now solution of heat conduction problems by Laplace transform. This example, use Fourier sine transform to solve this one. Del u del t equals to k into del square u del x square. This is the actually heat equation. Under the condition, there are given condition. First one is if the independent variable u 0 t dependent variable. This is the dependent variable u 0 t equals to 0 and u x 0 t to the power minus x. Actually, there are two variables, two independent variable. One is t and other is x. Okay. Actually, why this is partial? This is partial differential equation. This is partial differential equation because there are single independent dependent variable and if there are more than two or more than uh, two or more independent variable is called partial derivative. That means this is u is the function of xt. U is the function of what? Xt. U is the dependent variable and xt is the independent variable. If there are two or more independent variable, then the derivatives will be what? Partial derivatives. And if the differential equation form, then that will be partial differential equation. Remember it. This is why partial differential equation. Why? Actually, there are two independent variable x and t, and one is dependent variable. U is the dependent variable. U depend on t and x. Remember it. This is the rate of change of u with respect to time. But here rate of change of u with respect to x. With the increment of x, u is the changing. That means if x is increased, then u is also increasing, and if x is decreased, then u is also decrease. This is the rate actually with respect to x, and this is the rate with respect to time. You must know about the definition of partial differential equation. Remember it. Now the under the three conditions, u x t equals to 0. X is 0 here, but t is non-zero. U 0, t equals to 0, and u is the function of x, and but time here 0, t is 0. This will give the condition e to the power minus x, and uxt is bounded. Now the given heat equation del u del t equals to k del square u del x square. This is the equation number 1. Now taking Fourier sine transform on both sides. Taking Fourier sine transform on both sides. 0 to infinity del u del t sine sx dx. Then f of x f of x sine s. This is the sine transform of Fourier. Now this equals to k into 0 to infinity del square u del x square, just right hand side part, just sine sx dx. This sine sx for sine Fourier sine transform. Now du dt, this is the total derivatives. Du dt equals to total derivatives of u bar equals to k into second bracket su at x equals to 0 minus s square u, where u bar is the Fourier sine transform of u. U bar what? Fourier sine transform of u. This is why from this one we can write du bar dt plus k s square u bar. U bar what? This one. Just taking all in left hand side. Now ddt can be put at capital D. Capital D is the operator, differential operator. ddt u bar plus k s square u equals to 0. Now just solving this differential equation. Now right hand side is 0 for this differential equation. If right hand side is 0, then auxiliary equation can be written as m plus k s square equal to 0. Then m equals to minus k s square. Just complementary function. Complementary function can be written as just only one constant c1 e to the power minus this one. E to the power minus mx will be solution of a standard form, but e to the power e to the power mx will be the solution. But here independent variable is t, and independent variable is t. This is why, and the power will be in replace of m minus k s square. This is why e to the power minus k s square t. Then u bar equals to the solution will be c1 e to the power minus k s square t. This is the required solution, but t is unknown. T is unknown at t equals to 0, using the boundary condition. Using the boundary condition at t equals to 0, u bar, value of u bar from equation 2 equals to 0 to infinity ut 0 at value of u at t equal to 0 sin sx dx 0 to infinity e to the power minus x e to the power minus x sin sx dx. After putting t equals to 0, e to the power to the power what will be at u value what? U value this. After putting t equals to 0, we get e to the power minus x is the result. Then sin sx dx. Now e to the power minus x sin sx formula what? Using this integration formula, integration of e to the power my x sin bx dx equals to e to the power x divided by square plus b square sin bx plus sin bx minus b cos bx. This is the main formula. Using this formula, putting a equals to minus 1 and b equals to s, just we get this one, and this is the value of u at u bar at t equals to 0. Now from from 2 u bar at the value of u bar at t equals to 0 will be c1. T equals to 0, e to the power 0, e to the power 0 means what? 1. This is why u bar equals to only c1, just putting t equals to 0. Now from 3 and 4 we get c1 equals to what? This one, this c1 and this one equal same, this and this same, left hand side same from 3 and 4. This is why right hand side equals to right hand side. And from 2 u bar equals to what will be? Putting the value of c1 we get u bar equals to this one. Now taking inverse Fourier transform we get uxt. Inverse Fourier transform uxt equals to root over twice pi 0 to infinity just f of u, this u values, this function sin sx ds. Now uxt equals to 2 by pi root over twice pi, root over twice pi 2 times. This is why square and square root cancel. This is why 2 divided by pi 0 to infinity and s by 1 plus s square e to the power s t. This is the ux function. This is the ux function, u function. And this comes from Fourier transform, inverse Fourier transform. This is why 0 to infinity root over twice by pi. Uxt equals to this one, the given result. Hello. At t equals to 0, the value of u at t equals to 0, the value of u what? T equals to 0, at t equals to 0, the value of u e to the power minus x. This is why this one using the boundary condition.
স্যার নিচে নিচে root over 2/5 এটা কেমন আসছে?
root over 2
জি
this
স্যার
one.
এটা হ্যাঁ
Using
হ্যাঁ
from the definition of inverse Fourier transform, inverse Fourier transform definition of Fourier inverse Fourier transform. Using the definition of inverse Fourier transform, root over twice 2 divided by pi 0 to infinity, and this is the whole f of x, right? Fourier transform of f of x. This is the Fourier transform
জি
of f
স্যার
of x. But if we take inverse of Fourier transform, then this will be uxt will be this constant for inverse Fourier transform 2 by pi 0 to infinity, and this is the Fourier transform of u then sin sx ds. This is the Fourier transform of f of function u, Fourier transform. Actually you must know about the inverse Fourier transform. Similarly, the next example can be solved. The equation del u del t equals to del square u del x square. Here chi is absent, that means chi equals to 1. But there is a condition given, x must be non-zero and t also non-zero and non-negative also. Now subject to the condition u equals to 0 when x equals to 0 and t is greater than 0, time is 0 greater than 0. Condition 2, u equals to 1 if x lies between 0 and less than 1. But if x greater than 1, then when time t equals to 0, then the functional value will be 0. Value of dependent variable will be 0. Now, and uxt of course bounded. That means defined within a range. In view of the initial condition, we apply the Fourier transform on both sides. Look like before example, 0 to infinity del u del t sin sx dx, 0 to infinity del square u del x square. Just this is the f of x for this right hand side function, and this is also look like f of x function, functional value for the left hand side, and this is the Fourier transform. Now del t is the constant term for this 0 to infinity u sin sx dx with respect to x, and minus this is the this one comes from where? Comes from this value, this one, using Fourier transform derivatives. Okay, using Fourier transform derivatives, differentiation minus s square u bar s conjugate, using this one, this space and this article, that means second derivatives of Fourier transform minus s square u bar sx and plus s u of 0. On putting u equals to 0 and x equals to 0, we get del u del t plus s square u equals to 0. This can be written as del t plus s square, just taking u bar as common, equals to 0. In solution, the complementary function will be what? Before, like look like before example, a complementary function will be u bar st equals to a e to the power s minus s square t. This is the parameter s square, and it m because m equals to minus 1. This is why a into e to the power minus s square t will be the solution. Equation number 1. Now we have assumed u bar equals to u bar st equals to 0 to infinity. This is the uxt sin sx dx from Fourier transform. Now u bar as 0, just putting t equals to 0 here. Now ux 0 sin sx, but ux 0 equals to what? 1 for 0 to 1 limit. 0 to 1 limit. For 0 to 1 limit, u value what? 1 when t equals to 0. Now taking just a simple integration, sine integration what? Minus cos, dividing with the coefficient of x. The coefficient of x is s, because the integration is with respect to x. Now 0 to 1 limit, after putting this limit, we can 1 minus cos s divided by s. Remember it, ux 0 is the equal to 1, is this is the given condition, and we used here this one for this one. Now 0 to 1 is the given limit. Now from equation 1 and 2, we can write this value and this value what? A equals to u bar as 0 equals to this. After putting t equals to 0, we get u as 0 what? Only a. E to the power 0 equals to only 1. This is why a equals to u bar as 0. U bar as 0 equals to a. This is why this one also 1 minus cos s divided by s. Now on computing the value of a in equation 1, now putting the value of a in equation 1, we get the required result is this. Just putting the value of a equals to what? This one, 1 minus cos s divided by s e to the power s square t. Now applying the inverse Fourier sine transform, applying the Fourier transform, then this is the function, right? This is the Fourier transform. But if we take the Fourier inverse Fourier transform, this will be the inside the inverse Fourier function. Now inverse Fourier function of this one equals to uxt equals to 2 by pi 0 to infinity 0 to infinity 2 by pi. This is why 1 minus just this function one, Fourier transform of f of x ds. This is the total function represent inverse Fourier sine transform, remember it. And this is the required result. I hope everybody understand. Now solution of partial differential equation by Fourier transform. Uh, Similar example 42. Solve del square u dt square equal to alpha square del square u dx del x square. This is an wave equation actually, and second order partial differential equation. Partial differentiation, why? Actually they are dependent variable u, and this u depend on two independent variable x and t. That means u is the function of xt. U is the function of xt. That means they are single dependent variable and two independent variable. This single dependent variable depends on two independent variable xt. This is why it is called partial differential equation of second order. Remember it. With condition, the given condition ux 0 equals to f of x. This is the given condition. When t equals to 0, time equals to 0, then the value of dependent variable will be f of x. Now first derivative of first partial derivative of del u del t x 0 equals to, this is given g of x function, and assuming u, if this partial derivative of u with respect to x tends to 0, if x is very large, that means x tends to infinity. Now we'll try to solve this. Please concentrate, heart and soul. Now taking Fourier transform on both sides of the differential equation, look like before. Just take Fourier transform on both sides. Um, d square u dt square equal to alpha square. Alpha square means this constant. minus s square u bar. U bar is the Fourier transform of u. Remember it. We have already used u bar in replace of u to indicate Fourier transform. To indicate Fourier transform. U bar is the Fourier transform of u with respect to x. That means this differential equation can be written as d square u dt square plus alpha square s square u bar equals to 0. Now the auxiliary equation taking ddt equals to capital D operator, ddt will be indicated by capital D. Auxiliary equation will be capital D square plus alpha square s square. Just taking u bar common. Now this auxiliary equation, from this auxiliary equation d equals to what? Plus minus I alpha s. I what? If you take alpha square s square in right hand side, then there will be minus 1. Minus 1 can be written as I square, imaginary number I. If the imaginary number is I, then I square equals to minus 1. Then capital D equals to, we get plus minus I alpha s. Now solution can be written as partial solution of the partial differential equation. Given partial differential equation, u bar s t equals to a into e to the power plus I alpha s and b into e to the power plus minus I alpha s. Remember it. There are two roots because it is second order, and these two roots, one can be e to the power first root into t plus b into e to the power minus I alpha st. This is the whole solution of the given partial differential equation. Now using the boundary condition or initial condition, ux0 equals to f of x and del u del t x0 equals to, that means first derivative is equals to g of x, another function. Now u bar as 0, putting t equals to 0, this equals to f of s. This is also uh, u as 0, u as 0, and ddt, or if you take ddt, first differentiation of u bar with respect to time is 0 equals to capital Gs on taking transform. Now if we take these two function as Fourier transformation, then f of x will be transformed to capital Fourier transform of f of s, and this also can be transformed to Fourier transform, and this is indicated as capital Gs. Okay, that means this is the main given function for this condition. Then if we take the Fourier transform of f of x, then this will be f of s, and if we take the Fourier transform of g of x, then this will be the capital Gs will be the Fourier transform of g of x, small g of x on taking transform. Just using this condition one, in one, I am using this condition in equation 1, we get u bar as 0 equal to, that means putting t equals to 0, e to the power 0, e to the power 0, this is why only a plus b, right? And a plus b, the u bar as 0 equals to a plus b, this is also f of s, this one. Now du bar dt as 0, just putting t equals to 0, I alpha s a minus b gs, this is also given. Now solving equation 2 and 3, just solving for a and b, we get a equals to this and b equals to this one. Now using these two values, total solution of one will be u bar st equal to, taking half on from both, half a e to the power I alpha st plus half b e to the power minus I alpha st. Now by the inversion theorem, taking Fourier inverse Fourier transform, ux2 will be, we have to use inverse Fourier transform for this. Ux2 will be half f of x, s will be transformed to x minus alpha t minus 1 by alpha integration alpha to minus x minus alpha z of theta d theta. This is the third bracket plus, for same in the same case we using inversion formula, we get also this. Just this s transform to f of x plus alpha t, and z s transform to angle theta. Using the result, this equals to this. Total, actually this is the result. Actually this is the first differentiation of u bar with respect to time. That means taking differentiation with respect to time t. That means a into e to the power x formula, e to the power x, just dividing with the coefficient of what? Sorry, multiplying with the coefficient of t, I alpha s, multiplying I alpha s. Then similarly, b is the constant, e to the power e to the power x formula, e to the power x, but just multiplying with the coefficient of t minus I alpha s. That means a minus b and I alpha is the common. I alpha s is the common. Just putting this value equals to what? Gs. Gs is given. Gs is given. Fourier transform of the given function. Just taking first differentiation in one. In differentiation, we have to multiply with the coefficient of independent variable. Remember it. Multiplying with the coefficient of independent variable. But integration, in integration, what? We have to multiply. We have to divide with the coefficient of independent variable. Remember this one. Now another application to simple heat transfer equation, solution of heat conduction problem by Fourier Sine transform. Okay. Now this example states that solve del u del t equals to del square u del x square and x is greater than 0, t is greater than 0. Subject to the condition, this is the initial condition, u 0 t equals to 0 and u 4 0 equals to 0. Now and also u x 0 equals to twice x, this is given here. This is the given partial differential equation of heat. Now x lies between 0, x is the greater than 0 but less than 4, but t is greater than 0, subject to the boundary condition. These three conditions given in our question. Now this is the initial condition, remember it, not boundary condition, because initial value 0 is changing the whole function. This is why just using condition, initial condition. On applying Fourier Sine transform one, we get just putting taking Sine transform on both sets. Look like before example. Same example we are solving about. This is the fourth maybe. Now integration limit will be what? 0 to 4. 0 to 4 del u del t sine function will be what? S pi x divided by 4 dx. Actually pi x by 4. This is the, because the limit is given, not 0 to infinity. This is why. This is the periodic function. This is why sine and period will be pi x by 4 dx. 0 to pi 0 to 4. This also del square u del x square given, and this is the Fourier transform. If you take Fourier transform, then sine s pi pi x by 4 using the period of 0 to 4 dx. Now integrating by parts, integration by parts, we get ddt ddt 0 to 4 uxt sine s pi x by 4 dx equals to sine uxt. This is the Fourier transform of u function. Fourier transform of u function. This equals to del u del x sine s pi x by 4 0 to 4 limited del u del t del u del x sine s pi x by 4 minus s pi by 4 0 to 4 del u del x cos s pi x by 4. Now actually taking on both sides integration by parts. Integration by parts, del u del x taking integration. If you take this integration, one order will be decreased from differentiation. That means del u del x only, del u del x. Then u into b plus b into u. Just using this u into that means u into integration of b minus differentiation of this. Differentiation of this what? Differentiation of this will be cos. Cos, but with dividing with the coefficient of x. Coefficient of x what? S pi divided by 4. So 1 divided by s pi divided by 4. That means s pi divided by 4. 0 to 4. This one this one again integration. Again integration means del u del x. Remember it. Now this can be written as d dt of u bar s. That means Fourier transform of u equals to after putting the limit 4 here, 4 divided by 4 in place of x. If we put 4, then sine 0 equals sine pi. Sine pi means what? Sine n pi equals to 0. This way this whole will give 0 after putting upper limit. Now if we put 0 also 0, this way the total value of this function will be 0 minus now s pi divided by 4 third bracket this whole integration. Again integration what? Del u del x integration will be u x t cos s pi x minus ub process u into b integration. This integration what? Uxt. Del u del x integration what will be? Uxt. Remember it. Just the order of the first order differentiation derivative, first order derivatives will be decreased. It will give only function uxt. Then this cos, this cos. Now u into differentiation of b plus minus u differentiation what? U differentiation cos differentiation what? Minus sign dividing with the coefficient of s x s pi by 4. This is why dividing the coefficient of this. Now this whole integration just considering ub process u into b integration minus integration of differentiation of u integration of b, then third bracket. This equals to minus just putting the values upper limit and lower limits, we get this result. By taking 4 here, this will be 4t and 4 divided by 4 what? Cos s pi. Now minus 0, if we put 0 cos 0 what? 1, but u will be u 0t minus now this integration what? This integration will be uxt sin s pi t. This is the Fourier transform of what? Us. Fourier transform, this whole indicate the Fourier transform of s. Fourier transform of u, and this is the sine transform. Remember it. This why u bar s. Now s square pi square divided by 16. After putting the values, s pi by 4 will be s pi by 4 whole square. Now putting the value limiting value, that means given boundary value, initial value u0t u4t from 2 and 4, we get ddt Fourier transform of u equals to this one. This equals to this is the 0 from using condition, boundary condition, then this will be this one. Now imply 1 by u bar s dus equals to this. Now taking integration on both sides, this will give the solution u Fourier sine transform st equals to c into e to the power this is the ddt coefficient of ddt. This is why e to the power this, remember it, t, e to the power this t is the independent variable here. Now on putting t equals to 0, this will give c to the power 0. C e to the power 0 means 1, that means only c us as 0. Just putting you get t equals to 0, this equals to what? C only. This whole give 1 because e to the power 0 equals to 1. Now c equals to this one. Again Fourier transform of s t equals to 0 to 4 u x t sin s x dx by 4. By definition, Fourier transform definition, we get this equation 6. Now putting t equals to 0 here, we get Fourier transform of s0 t equals to 0. Then this will give ux0 sin s pi x divided by 4 dx. Now taking this integration, but this equals to c, remember it, we have already proved this equals to c. Now c equals to 0 to 4, this is what? ux0 sin s pi x by 4, since c equals to this one. Again ux0 equals to given twice x, remember it, from the given boundary condition. 0 to 4 ux 0 equals to twice x sine s pi x divided by 4 dx, and u transform to x, remember it, u transform to x because the functional value is twice x, this is why. Now taking integration ub process integration, what, uh, 2x twice x will be u, and integration of sine what, minus cos dividing with the coefficient of s pi by 4, this is why dividing, this is why this will be 4 by s pi, and this minus differentiation of twice x, what, only 2. Now this again integration, this is integration, this integration what, sine and with dividing with the coefficient of s pi by 4, that means s pi by 4 how many, 2 times, this is why 4 by s 5 2 times, this is why 16 by s square by square, and this will be sine, just putting upper limit and lower limit of integration. Integration by parts, that means integration of ub dx using integration ub process, just putting the upper limit lower limit, we get this one, this equals to this, remember it, cos pi equals to minus 1, cos pi equals to what, minus 1, how many minus 1 here, minus 1 to the power 5, minus 1 to the power 5, minus 32, just multiplying s pi, you get 32 divided by s pi, minus 1 to the power how many, s, this will be s plus 1. Now putting the value of c in equation 5, in 5, this is the 5 equation, we get u Fourier transform of sine transform of st equals to this one, just putting the value of c gives equation 7. Now taking inverse Fourier transform, look like before example, inverse Fourier transform of us sine transform will be uxt equals to 2 by 4 summation 2 by 4 what, 2 by pi, but in our standard definition 2 by pi was, there was 2 by pi, but pi equals to pi means what, 4, period 4, this is why 2 by pi s equals to 1 to infinity usx dx sine x, using Fourier sine transform, this one, and this gives the u Fourier sine transform of st equals to this, this is our result, this one, using 7, and this gives the whole solution of the problem, a little bit lengthy. Similar process, example 44, using Fourier sine transform, we have to use, you have to solve this partial differentiation heat equation, and using this boundary condition, initial condition is this. Now taking Fourier sine transform, just as like before, and making a differential equation, auxiliary equation, using auxiliary equation we get the solution of this u bar, this one equals to this, just plus c is the integral constant, using this the given boundary condition, we get from equation 1, we get this one, this is the solution. Now practice it at home, if you don't understand, tell me next day in next class. Similar process, we have already solved, look like this problem, heat equation. Similarly you can solve this one, this left for you, this two.
Okay, sir.
Now finite Fourier transform, just within 5 minutes we will try to understand this. What is finite Fourier transform? Let f of x denote a function which is sectionally continuous over the range 0l. Actually 0l is the total limits given, but sectionally continuous. Sectionally means this limit can be divided into many parts. Then the Fourier finite sine transform of x on the interval is defined by f of s p, and equals to sine transform of Fourier finite sine transform. Remember it, finite sine transform will be 0 to l f of x sine uh, pi x p pi x divided by l, where p is the parameter instead of s, in previous Fourier transform we used s is the parameter, but in replace of s we use p for finite, to denote finite Fourier transform. The inversion formula will be like this. F of x equals to, just f of x equals to, this will be again will be go in left hand side, 2 by L, p equals to 1 to infinity f of s p, f of s p sine sine this one. Now proof, very easy for you. For the function, for the given function f of x in 0L, if we find the half range Fourier sine series, from Fourier series, Bn is the sine coefficient, Bn is the sine coefficient, sine and pi x by L, where Bn equals to this one, from Fourier series we get this one. And for in replace of n, p, with the replace of p, we get 2 by L, 0 to L, f of x sine p phi x by L dx. That means 2 by L Fourier sine finite Fourier sine transform, finite Fourier sine transform, this one, by definition. This way, substituting it in one, we get this is the, this is the what, finite Fourier transform, this one. So just two or three lines, this theorem is proved. Now similarly, Fourier cosine transform, just cos, we have to use cos in replace of sine, same p parameter p. Proof also same, this is left for you. An example, find the finite Fourier sine and cosine transform of this, f of x equals to 1, f of x equals to f of x, f of x equals to x square, f of x equals to 1 if this range, and f of x equals to minus 1 if this given range, f of x equal to x cube in 0 to L, f of x equal to e to the power x if this given. Now just a little bit easy for you, very easy for you. Just put just using Fourier, finite Fourier sine transform, finite Fourier sine transform of 1 equals to, the in replace of p we use 1 here, 0 to pi 1, f of x equals to what, 1 sine p pi x divided by pi. That means just taking integration with respect to x, only minus cos, sine integration minus cos, dividing with the coefficient of x, pi pi cancel, p, this is the result. Now cosine transform will be just using cos, this is the result. Similarly, inverse Fourier transform of, as we inverse finite Fourier transform, this 0 to L function will be x, this is the given. Number 2, f of x equals to x. This is why UB process, integration, UB process, u into integration of b minus differentiation of u, integration of second times integration of b. This is one. Now similarly, you can, I hope everybody will answer this using
স্যার
finite
আপনি না
Fourier
বললেন স্যার
transform.
এক্সাম্পল 45 পড়ে যাবেন না, এটা এক্সাম্পল 46।